Oh, are you sitting here?
No, I'm sitting on the
Okay.
So we have a
So not right now, I don't think. Yeah, no. Okay, well, okay, was something watching that or? So I'd be happy to send an email and forward the link, but I don't know who it is. Yeah, sure. Was it just this morning? No? Let's do that. Yeah, sure. I know, yeah, no, no worries.
Hi, good morning, everyone. It's such a day off. So I'm Erin. We'll get introductions in a second. That was very exciting. Mike is just setting up his slides. I know there are a few people who are still in the process of getting here this morning. But make sure you have extra copies of the papers and materials and kind of come by and see them. And make sure that it has been used as well. Yes, we're here.
Yeah, sure. Yeah.
Wow, makes it a good story.
Okay, good.
All right, so you need to Jared. Next one, really like testing your relationship.
You can make it all in the wedding now. You can do a chance for it now.
Right. Awesome.
So fair.
Okay.
I told him, I said, I don't even know if you want to be the smartest man I've ever met.
Yeah, and so it's just kind of fun, you know, so one question, you know, we should work at the next, always, all the, but it is, like, you know, and that's good. Lessons that you can learn in the things that you learn about technology, you know, data. Thank you so much for yeah. Okay, great. So, everyone hear me? I just mic up. I can project reasonably well, so I'm not too worried about the microphone. Well, good morning, everyone. Thanks so much again for joining us in San Diego. Academy Health, and I'm really pleased to actually be back at my alma mater. A lot of years ago, but I was saying to my wonderful colleague Nina that actually it's become a full-fashioned cycle. Students are exactly the same as they did left. So I think that's pretty hilarious, actually. Just to go back to again, thank you for joining us. I think today is going to be a really terrific set of discussions, and really want to start by thanking our hosts. And now this is a new technology for me, really. So I really want to start by thanking our hosts from UCSD, Shashin Zhang, his college Sean Wang, and the Department of Biomedical Informatics, which is Bill Machado is the chair. This is really, I think, a tremendous opportunity to work with some of our colleagues who participated in the forum in the past to bring people together. I know we'll have some of our colleagues from UCSD who are joining us throughout the day, so I think that's really fantastic as well. So my charge this morning is just to open the day. Our project officer for the Electric Methods Forum, Brady Arnava, will be joining us around 11 this morning, and we'll leave some time for him to make full remarks later in the day. But you know, his commitment and the agency for research and quality's commitment to bring groups of folks together from interdisciplinary perspectives to talk about the core issues that are really going to drive our ability to have interoperable running health systems is a key aspect of their mission, particularly as it pertains to improving quality and improving patient safety and ultimately generating more value in the system. So why don't we take a quick second to look at the agenda, and then what I'm going to do is I'll give you a bit of an overview of the forum for people who aren't as familiar and then we'll go ahead and get started with some presentations. So we'll start obviously with the welcome. I'm going to provide, as I mentioned, an overview of some activities the forum has been engaged with for context, because one of the things that we really want to encourage everyone who participates today to do is to think about ways to use other levers that the EDM forum has to advance discussion of the topics we're going to be discussing today. And then I'll turn things over to Shashan, who will talk a bit more about some of the projects that he's been involved with the EDM forum, particularly as they relate again to the topics we're going to discuss today, and especially on Daniela and Jerry's paper. And then we'll give Daniela Meeker from RAND and Minnesota University a chance to give an overview of their two methods papers and how they really intersect. A nice kind of big picture view. And then what we'll do is have a quick break and then head into breakout sessions where there will be discussion of each of the individual papers. And those of you who have been, everyone in the audience has been, all our participants have been assigned to particular discussion groups. And so there'll be more in-depth opportunity for discussion. And then we'll actually come back after a networking lunch for further discussion of those papers at the end of the day for more reflections about how we can move this set of topics forward as a group and take this out to the other collaborators that all of us work with. So that's the general overview for today. And Shashank, you want to say at the outset?
Sure. Fine.
And then I'll just, do you want to do that now or after? Okay. So I'll turn things over in just a second. And then other kind of quick notes. So my colleague Charya, who sort of made earlier, if you have any questions about materials or follow-up, or yours that you can talk with her. Our other colleague, Courtney Siegel, who many of you have heard from, is actually running late, and this is a great story, even though I'm sorry it's happened to her. She got stuck in Washington, D.C. Actually, the reason that our crew is running late is to produce the material she has in her bag. She got stuck in Washington, D.C. because 3,000 pounds of sand in an Alaska Air flight shifted en route out to D.C., spilling all of her everybody's bags and essentially exploding in the plane. So I mean, there are not many instances where you can blame being late on 3,000 pounds of sand. So we'll have to give her a little bit of that back when she gets here, but I think she's been fine. So I'm going to walk through this presentation really quickly. It seems to start going forward. So I've already introduced that the EDM forum, is a project funded by the Agency for Healthcare Research and Quality, really with the objective of generating a lot of the tools, methods, and data that are needed to drive health systems of the future. And I think, since 2010, when we started this effort as part of the Recovery and Reinvestment Fund, stimulus funds for effectiveness research, they're connected to a number of large registries and quality improvement activities and obviously effectiveness research projects. I think we demonstrated some pretty notable successes in terms of bringing different groups together, including our colleagues who are part of the standard project at UCSD, which includes Shashan and Daniela. So, one of the things that we talked about with our audiences is that the goal of running health systems is really for each individual encounter to contribute to new information that improves the health of patients and populations and subsequent interactions. And we know that we're obviously a fair bit away from that. And so we know that big data and big science have to contribute. There are a lot of practical challenges. And so the EDM forum and the communities that we work with, and now we reach out pretty regularly to about 2,500 folks across the country who are really interested in these issues. We're trying to think about how these data and methods, and particularly the evidence synthesis of the experiences to date, is going to really be, can be supported in this growing field. So we like to say that whether, an important distinction actually in the second phase of the EDM forum is that it's not just about thinking about research and discovery and kind of specific quality improvement projects in a narrow sense. Whether we're working with folks who's interested in improving the efficiency of healthcare operations, improving clinical quality, thinking through the comparative effectiveness of various treatments or how to improve patient centeredness in a lot of these settings, or thinking more broadly about how to improve the health of populations. All of these common challenges really exist. And so there are 4 ways that we have developed to work with a lot of the key contributors in the space, across the public and private sector, to spread and scale a lot of these innovations. And I think that, again, is particularly important at this juncture because the rapid research and quality improvement, particularly at the federal level, and by my count, kind of conservatively, we're at about $500 million in investment in the space at this point. The challenge is how we disseminate and really translate the key lessons learned from a lot of those projects so we don't keep doing the same things over and over again. So some of our colleagues refer to this as being an actor-oriented architecture, where we kind of create the goals for the community and then we create a number of mechanisms to make it easier for folks to share those lessons learned. So one of them, obviously, is that we made publicly available, this is critical to our promise to the agency of healthcare research and quality, we made publicly available and for free everything we produce, whether it's issue briefs or summarizing the various vocabularies that a lot of different actors in this multidisciplinary field are using. So we've got issue briefs, we'll talk about a ton of papers, there's webinars, et cetera. So there's an opportunity to really learn from all those experiences. And then we conduct a number of workshops, such as this, and maybe means the year over year, but actually that symposium is coming up on Friday, and if anyone wants to, I think all of you are signed, or on Saturday rather, and I think most of you are signed up to participate in that. But if not, let us know, and if you're interested in sticking around, we'd love to have you join us for that. But really, these key opportunities to connect with those in the field are invaluable. We've created a mechanism for more formal collaboration. We know that often to get people out of individual silos, it doesn't take a ton of direct support for individuals to do this work, but there does need to be some level of time that can be preserved to really do high quality work in the space. And so our collaborative methods project mechanism is designed to bring what I can refer to as uncommon bedfellows together to think about the kind of ready issues again that are impacting interoperability. And the next call for collaborative methods projects will close on June 18th. And I think we're going to get some really interesting proposals. If anyone's interested, I'm happy to talk more about some of the projects that we supported this last year. The methods papers that we're discussing today are a part of that set of activities. We've also been funding an effort called CLO, which is really a collaborative computing environment. We're working to set up kind of a common platform, app store model that will deal with a lot of security issues that folks face in the space, but we're really a good place to bring code and data together to task various approaches and make them more rigorous over time. We've also been supporting work on portable consent. So some strategies that have been pretty successful in the genomic space, and where we'd like to actually see more clinical research networks to reach out to patients and get them more activated and actively involved, not just in e-consent, but in this portable consent process that will allow people to granularly identify that they want to share their information for the purposes of bringing together genomic data, patient-reported data, and clinical data that will have the most sort of predictive value. And then we've got a number of opportunities for publishing, both in sort of non-peer-reviewed, doing open access types of opportunities. Our repository base to bring together a lot of governance strategies and documents that are used to promote sharing of data and sort of safe and secure, but still relatively open ways through our repository. But most importantly, we created this open access journal, EDM, which is peer reviewed. And we're just about to publish our 40th paper. EDM has been around for about 16 months. And I think has been generating a lot of positive traction. I think we've got 170 authors familiar with more than that.
We've over 389 authors and 170
So highly collaborative papers that really identify the kind of opportunities that are available. And our hope is actually that the papers that we discussed presented today and that perhaps some other papers that all of you are interested in writing on similar topics could be part of EGEMs. And Randy and our authors and as are many others of you in the group. And in total, I think what we've done is we've demonstrated that it can actually be more of a marketplace for kinds of ideas that will generate the tools and standards and so forth that will help achieve this goal for your evidence and learning health system. And again, already we've generated more than 160 resources in the space, and we know they're reaching thousands and thousands of folks. So again, just to close by thanking the AHRP for their continued support of the EDM forum and all of you for participating. So with that, Shasha, I'll turn things over to you. Any quick questions for anyone I should ask? Okay.
Welcome everyone, and thanks Aaron for the opportunity to contribute to the EDM workshop. And actually, I was a lucky participant of the two early EDM commissioning projects. So I would like to take this opportunity to share my exciting experience in involving. So particularly, I will talk about making distributed model accessible and useful to data analysis, which was carried out last year. So the basic idea is data sample is important to biomedical research. So a lot of time, single institution have limited sample to a specific like say rare disease. However, putting together all institutions have security and privacy concerns. But here we want to provide researchers a set of tools that enable efficient global data analysis without accessing patient level health record. This EDM forum commission project provides us an opportunity to assess the viability of distributed model, to build model without sharing data. So just a quick overview about the general idea of distributed analysis for like semi-answer primary mesh model like the generalized linear models. So assuming two institutes have separate private data set A and B, they can build intermediary statistics. And without sharing the raw data, they share the individual statistics with a centralized agent, which calculate the global parameter. And these global parameters are feedback sent back to the institutes to start another iteration of calculation for the intermediary statistics. And this process will loop in time until the global parameter converge. So this is basically the underlying idea of our project, web-based read-logistic regression model. Which leverages the intermediary statistics without sharing the raw data. So here is a little bit involved to calculate the log likelihood function and the second and first derivatives. Our omitted details and interested audience can look at our JM paper. So with the EDM forum support, we developed a web service for this theoretical model to put a grid logistic regression into practice. And through this project, we learned a lot. And we first developed the command line version of this protocol, and no one used that because people find it inconvenient. Also, institutes are not willing to open a specific port to be shared with other institutes. Then we tried to use a web-based approach. So we developed the Java applet and the JSP-based model that treating individual browser as a virtual machine. And the virtual machine can communicate through browsers of other participants without open a specific track. So it's going through the HTTPS, which most institutes by default allows. However, even so, this web service has not received a lot of assessment. There's additional concerns we figure out beyond usability and interface. So a lot of times people are not only concerned about like the model and the accessibility, but they also think about interpretability. How can they integrate this module seamlessly with the existing platform? How does this module talk with like the other module like data harmonization, integration? So we were thinking like even we provide a suitable tool like this, it might not be enough. In addition, people also think about other things like institutional privacy. For example, the aggregated statistics can leak information, for example, like infection rate in the emergency care. So even though the data will, the intermediate statistics may not leak individual privacy, it might be a problem to institutions they are. So these papers have replaced our effort and paddles and trying to address various concerns in privacy, efficiency, institutional concern, and UI, and we are summarizing our implementation challenges in a recent submission to EDM, which is still under issue. And with this in mind, we were thinking about moving to the next step to address the social factors and concerns about individual and institutions. So I move to Dr. Wang, who will talk about our project beyond the law.
Hello everyone, I'm Sean Wang, a postdoc researcher at the Division of Biomedical Informatics at UCSD, and I will discuss some potential extension beyond the law in the rest of this presentation. One question in collaborating data network is how to collaborate more efficiently and securely. Here we can interpret efficiency as the ability to get a certain amount of collaborative study in a cloud environment. And we also want to keep the data secure. Here, the security means the public cloud cannot share any information about the underlying data protected by some cryptographic technique. So, although the traditional encryption method can protect the data during the storage and transferring phases, they cannot be used in the proposed scenario, as the encrypted data must be decrypted before performing any data operation. So it turns out the recently developed homomorphic encryption method can be used as a candidate to achieve our goal. Where certain type of operations can be carried out directly on the encrypted data with the encrypted output. And only the person with the key can decrypt the result. So let's take a step back and look at the analogy of the analysis mechanism to better understand the homomorphic properties. Suppose the analyst has he wants to ask the worker to assemble a raw material into an necklace. However, analyst is worried about theft. He wants the worker to process the raw materials without having access to the raw materials. So the solution is that analyst lock all the materials in a black box. Then she asks the worker to assemble the necklace in the box. And when the work is done, analyst can unlock the box to get the necklace without worrying about it. So let's get back to the homomorphic properties. In homomorphic encryption, it's analogous to putting things inside the box. Everyone can do this operation, just like put a mail into a box. And then the house data privacy can be protected by homomorphic encryption. So the homomorphic encryption are taking the result out of the box. Only the person with the decryption key can perform this operation, such as authorized researcher or some authorized stakeholders. So the last is a homomorphic evaluation. It's analogous to working on the raw materials, but within the box. And everyone can do this operation. For example, one can compute the encrypted data in a cloud environment without sacrificing the data privacy. So I hope you have got a big picture of the homomorphic encryption. Now let's take a look at what can they do now using homomorphic encryption in practice? There are mainly three different types of homomorphic schemes, where each scheme has some trade-off between the flexibility and the complexity in terms of the computational cost and the type of operation that a given homomorphic encryption algorithm can support, respectively. On the overlap, we have a partial homomorphic encryption, which enable either addition or multiplication operation on the encrypted data, but they do not support both operations. So the partial homomorphic encryption has a more flexibility, but it also offers more complexity. So for the able the homomorphic encryption in the middle, it can support a certain number of both addition and multiplication operation on encrypted data. But as the total number of operations exceeds the threshold, the encrypted data cannot be processed anymore. And on the top right, we have fully homomorphic encryption, which offers the unlimited number of addition and multiplication operation on encrypted data, but with the cost of highest complexity. So we would like to identify some challenges and provide some potential solution about utilizing homomorphic encryption in practice. The first thing, we should support more types of operation. By default, the homomorphic encryption only support the basic operations such as addition, multiplication, or bitwise shifting operation. We can resort to some approximation method to support the advanced operation beyond the addition and multiplication operation. For example, the algorithm or exponential operation can be approximated by the first expansion, which include only addition and multiplication operations. And we can also need to support the floating number because the homomorphic operation take place on the integer. So some potential solution is to use fixed point approximation. For example, there's a floating number 0.5 can be represented by an integer of 128 with respect to a base 256. At 0.5 to 128 over 256. And finally, is about complexity issue. Homomorphic encryption usually are computational demanding, so we can resort to the parallel computing to speed up the homomorphic encryption, or we can leverage three different types of homomorphic schemes in different use cases. So here is some of our future work built upon the homomorphic encryption technique. We propose to the homomorphic encrypted federated cloud computing framework, which involves private cloud at each institution and a public cloud. And user can encrypt their private data and collaborate with other center, institution, and even public cloud without worrying about the data privacy, because the data privacy is protected by homomorphic encryption, and the encrypted data can also be processed by the public cloud or other institute. So, thank you. This is the rest of the agenda of the rest of this workshop. And, any questions?
Question I might ask this question. I know that there were a lot of lessons learned in the first project related to the conditions under which partners might or might not be willing to share data in the environment that you all have described. So I'd be curious, could you say a little bit more about that? And then, this discussion of sort of the next stage, how would you sort of practically address those challenges to set up, homomorphic encryption, with other partners in the future?
I see. So one limitation is some institution requires human in the loop to approve even intermediate statistics to lead their institute. They don't about any level of derived information. For example, VA, they cannot apply directly on mechanism because even we calculate the gradient and derivative, a person has to sit and click the button and say yes and this info. But our procedure requires automated way that synchronize multiple institutes. So in that case, there will be a limitation to include a copy, which requires human in the loop authentication. So in the future, I was hoping that this homomorphic encryption technique will allow institutes to put their data without considering about confidentiality, because the data by default is protected by encryption, and encrypted data will not leak the raw information. So without authentication, people cannot decrypt and see the raw data. And even the final output of this encryption, homomorphic encrypted data, the solution will be encrypted. So the output is encrypted as well. Upon approval of all institutes who participate, people cannot see what's being calculated. So that provides further layer of protection on institute privacy as well as the data confidentiality. But that comes with some computational cost, which is the research question we try to address.
So it's,
Yes.
it's a little unclear to me. So if the whole process is encrypted,
Yes.
right, then how do you learn about the data? You just trust that the inputs are good and clean, and you just run your models? It's not your healthcare data. You use that capacity.
So you're talking about the data harmonization and the pre-processing step.
Right. I mean, there's a lot of work that has to be done before we get to the analytic stage of any healthcare data analysis.
Right. We can. Yeah, I totally understand that. And in the current model, we don't have a data harmonization and pre-clinical step. But I know several other projects have been working on that. We can build the same federated model for data harmonization in the homomorphic encrypted manner to pre-process the data before they're usable.
So why did you guys focus on logistic regression? Is that the main analytic reason?
No, logistic regression is just a use case because the typical generalized linear model. We actually also developed the cost proportional hardware, which is a non-parametric model. But non-parametric models are more involved, so that most times we have to do one by a case. And logistic regression model is more general.
Sorry, I'm new to this word. I come from, I work for IBM. People are just going to do what they have to do. They're not going to wait for encryption of this kind or that kind. There's already things that SQL servers have built at multiple levels of encryption that are already the basis of companies that are helping other companies work with large amounts of data. So here, I guess the challenge is you have different entities and you want them to be able to trust each other. And my experience has shown it's basically consensus has to start moving in the direction that we actually start trusting the answers that come from those exercises. And often merging two different data sets and learning from them gives garbage answers. So until we get to the point that we get the methods, the statistical methods correct of how to infer from various distributed data sets, no one's going to trust or put in enough effort into trying to understand how we can collaborate properly. So in some sense, the encryption seems to be less of a problem, and it's the statistical analysis part that's a bigger problem. How do you gain share from people into understanding and agreeing that the answers are correct?
Healthcare, for years, we've had distributed networks where data are summarized.
And it's known that you can give me any summary statistics. It conveys almost nothing about reasoning, and the answers will be totally opposite. So, in some sense, I think that's our real challenge in some way, which is how to.
But that's what we want to know. That's one of the things that's super important in healthcare is if, like OMA and some of the other groups, maybe Sentinel, Regional Research Network, if there is, effect level heterogeneity across the distributed networks, that's a super important thing to find. So we don't necessarily have to have the effect consistent across all the organizations for all the different data partners.
No, I'm not talking about the effect. I'm saying how do you even reason about it? I don't think anyone really knows how to reason about it. It's just, there is the RCT world on one end, the randomized computer world, and there's the observational, studies, at the other end of the spectrum. And I think we have to reason about where those sit in this larger picture of us trying to learn about healthcare data and healthcare systems. And there'll always be this resistance to trying to take observational studies and on large data sets and make inferences about them and use them as actual policy. And as long as that doesn't happen, all I need to say is technology is not the real problem here. It's the underlying foundations, the mathematical foundations that are, and of course,
And the biases of people.
and the biases.
Right. But let me give you a case when this technology will be useful. For example, there's UCSD researcher who's in the driving biology project of IH, and she's working on coagulability disease. Very limited coagulability disease is early childhood heart disease. Can you hear me now? So there's a PI who worked at UCSD on Kawasaki disease, which is a rare childhood heart disease. We have a very limited sample, dozens of samples at UCSD, and she has all these high-dimensional genetic data. Using these, you did not come up with any conclusion which is statistically robust. But collaborating with Singapore, Japan, and other countries which has abundant cases, she can actually derive model and find biomarkers. However, these countries have strict policies, say like the data has to be protected in a privacy-preserving manner before you can run these analyses. And so in that case, so I agree with you. For some certain cases, meta-analysis is sufficient. Actually, we did some case study using ProofCare network on some IBD disease. So the result of this distributed logistic regression is very comparable to just the meta-analysis, combining parameters based on the weighting of the sample size at each institution. Because you have a large enough sample, so actually each individual sites have captured enough pattern, and the pattern is robust. So combining these doesn't increase confidence interval, so that doesn't make too much difference. So I agree with you on the population-based study or large clinical trial. You probably can leverage local institute to conduct the study. But for phenotype which are rare, which I was mentioning at the beginning, those distributed models can help a lot.
Well, don't get me wrong, I'm saying people would come up with the appropriate business paradigm to make that happen once they're convinced that it is necessary to do it. For example, people will say, give me your analytics and I'll run it in-house, and then I'll give you the results. The analytics can be as complicated as you want.
Right.
But you can't take my data, right? So that's another model where basically, and that's something that people have already started using because you're never going to get the contracts or the privacy concerns because it's actually a lay person, a politician who's worried about it. And no matter of math is going to convince that person that something can't go wrong.
Yeah. So, Mike, you have totally set the stage for today because your questions are exactly what the two papers that we'll hear about from Mike and Danielle are going to address. First, from Mike, what is the paradigm for clinical research, and then how do some of these techniques, particularly from an evaluative framework, fit in? And then from Daniela, to kind of add in work with Shoshen on some of the statistical issues. And then I think throughout this, though, we need to come back, from my perspective, to two questions. One is sort of what is the acceptability and willingness of people to sort of enter this space at the early stage and do the kinds of experimentation that you're describing that will get us closer to figuring out the answers to these questions. So I would like to invite everybody to really think about that question. What are, not the pilots, but what are the sort of larger scale implementations of these types of questions that would have meaning and make a case for doing this, where there are opportunities working together and across all the projects that everybody in this room is connected to. And then, what is the sort of additional pathway in terms of, work that needs to be done, on the statistical side, on the governance side to get us there, because we need to sort of look at what that glide path is.
Yeah, in response to what you were saying, just to validate, I think you're right that there are serious credibility issues with non-experimental research, and that may be part of the discussion as well. What's the analytic framework to improve credibility and actionability of research?
Yeah, absolutely. So, any other questions you guys?
Yeah, let me hand over to the next speaker.
Okay, so I think Mike, you are.
Actually,
Do you want to make a comment? Oh, okay. Have you guys? You switched things up.
Yeah.
Okay, fair enough.
I also just wanted to mention that the difference you ever kind of the last half of the discussion that it
Oh while you're getting set up, personally, we did not make a formal time for introductions this morning because we know everyone will be in small groups this afternoon. But it might be useful, I think, as we were just discussing, we have intentionally brought folks together from very different perspectives, some who are not as closely connected to healthcare. So even just if we could go sort of down the road and people could introduce themselves sort of in general, your background, and then which institution you're from, that would be fantastic. So Yelena, do you want to start? And then we'll get back to you, Danielle.
Sure. Yelena Zurak from Mathematica. I am a methods person, trying to be. I've been working on quality improvement quite a lot, evaluation studies, quality improvement initiatives in hospitals, most recently more primary care redesign.
Randy Brown, I'm the Director of Research at Accomplishment Mathematica, and where I've been for about forever. And the main thing that I'm working on this area at the moment is that CMS is funded for improving primary care practices.
So I'm Gareth Parry from the City Sciences Institute of Healthcare Improvement. I'm doing a lot of work. I'm leading our external evaluation efforts at the NHI. So I've been doing a lot of work thinking about how you implement methods for evaluation of quality product initiatives.
Dennis Rustic, and I'm at Harvard Medical School, and I'm the Director of Research at the Department of Program Healthcare Institute. I'm here actually, I think, primarily at Mike's invitation because of work that we've done for many years on interrupted time series. With interrupted time series in a variety of contexts. But coincidentally, actually, our department is the coordinating center for both Mid-Sentinel and also PCOR net. So I have a lot of experience over the years in the history of why the distributed data initiatives wound up looking like they look right now, actually. So I think not so much on the statistical side, on the practical logistics side, I think, which is part of the issues that you're talking about, I can contribute to some of the discussion there.
I'm Jiang, biomedical informatics at UCSD. My research interest is health privacy and data analysis.
And again, Erin Holby, I'm a health services researcher by background, and for the last 7 years or so, I've been working with the future of research in health services is going to look like, and principal investigator of EDM Forum.
I'm Sean Wang, a postdoc researcher at Division of Biomedical Informatics at UCSD. I'm working on the distributed model learning of some encryption happening to protect the data privacy.
I'm Feng Zhen. I'm an internship in UCSD here, and I'm hacker. Thank you.
Good morning, I'm Beth Devine. I'm an associate professor at the University of Washington in Seattle, and I'm a health services research methods scientist, and have the privilege of working with Erin in the AHRA-funded AHRQ enhanced registries for QR to CER, where I was involved in health information technology. So really validating the quality of electronic reproductive data.
Hi, my name is Mayank Sharma. I'm a researcher at IBM Research and applied mathematician at the electrical engineering at training. And I kind of take the, as part of IBM Research, we do a lot of projects, which range from energy systems to resource allocation networks. And more recently, I've been looking at healthcare systems. And again, I'd like to bring some of the sort of statistical and rigor systems thinking into this whole field, so that we don't lose sight of the fact that technology is just technology, but it's the methods that really matter.
This is your crowd.
Hi, I'm Jay Vaidya. I'm an associate professor at the university, and I'm really interested in security and privacy and data analytics, both from an individual privacy perspective, but also from the organizational access control perspective.
Hi everyone, I'm Mike Stoto. I'm a faculty at Georgetown. I'm a statistician by training, and I call myself more a health services researcher now. I'm kind of hard to pin down the kind of things that I've done though. A lot of my work has been in public health systems, but I've been working with EDM Forum since the outset, working on some methods issues, and we'll hear more about that.
Hello, everybody. My name is Pat Ryan. I work at Janssen Research and Development, where I head up our epidemiology analytics group. And I think we're a couple hats today as one of the investigators of OMA, and now we have a effort called Odyssey, which is an open source collaborative to support distributed data networks. And I'm also a member of the EDM Forum Steering Committee.
Hi, Alyssa Priest. I'm from Baylor Healthcare System. Sorry, we've just merged. Back here from Baylor Scott and White Health North Division in Dallas, Texas. Baylor Healthcare System recently merged with Scott and White in fall, so every couple of weeks we have a new organizational chart and a new title. So my background is in epidemiology. I focus in my previous work life, I focused on doing data management methods in clinical trials, and developing useful tools for epidemiologists who aren't actually taught how to do any data management in their training. So my interests are in data management tools for maybe smaller focused research, clinical effectiveness research, epidemiologists, anyone who hasn't been formally trained in it, and then also data quality issues resulting from the data.
I've been working on applying machine learning and data mining to research literature for data mining and theology for recently I was intrigued by the idea to mining data from elsewhere. That is this chance to
Jared Murray. I'm a statistician. Most recently, I was at Duke University as a postdoc after I finished my PhD, and I'm actually transitioning to a visiting position at Carnegie Mellon, also in the staff department. My work focuses on sort of data complication problems. So missing data, combining data sets, making causal inference from data. That's sort of anticipation from solving those problems.
Hi, this is Arya. I'm first year PhD student in methodology and UCSD on this. And yeah, I'm interested in machine learning. Problems.
Geologist and mathematician. I primarily identify with BA. I'm on faculty at the University of Utah as well. And most of the work I've been doing lately is development of what we call trust moduli, things that we're going to talk about today in that OMA and other groups have done, where we're building transparent, reusable database systems.
Morning, I'm Charles Bailey. I am from the Children's Hospital of Philadelphia and University of Pennsylvania, where I work with one of the CDRNs that are part of PCOR, as Dennis mentioned, the pediatric network there. And I think I'm in large part testimony to the audience, and I am probably the mathematical lightweight in the room. I am a bioinformaticist and medical informaticist by background, and focus on characteristics of data derived from electronic health records, and working on both their utility in applied effectiveness research and their utility in their citing close to clinical practice, and so keeping a short loop between drawing inferences and applying them.
Awesome. Well, thank you all for taking that time. I'm going to grab my stuff and move it here. And then Danielle will turn over to you. We'll catch up, I think, with our time this afternoon. So I think that was really great to go around with you all.
Yeah, right I decided to places in the order because in many ways of the work is moving backwards and starting to deeper. More things that involve when we start talking about the kinds of things that we're interested in exploring here, and like I said, I love Jerry finish. So I'm going to talk about this first part of things, which is how federated research networks and big data frameworks works for evolution and what kind of opportunities are available. And Jerry's going to then speak more about some of the statistical rigor that I think we need to apply in order to merge these two histories effectively. So, and I have this slide up to distinguish between two different paradigms. So far, most of the clinical data research networks at best we've been applying this kind of meta-analysis approach to distributed analytics. And in this model, you could have some kind of a query portal that would distribute a query or a program to different data holders. And each data holder will return one model. So you get a model for each site that you compare across the data. This is pretty similar to a meta-analysis that people have been referring to as meta regression and the analytic regression. And that's to be distinguished from distributed analytics where you apply the iterative methods that Shashan described in order to fit a single model that merges data effectively from different sites. The algorithms in order to implement distributed analytics take a little bit more complexity to play. And I think that Shashan didn't go into too many of the details. I'm also not going into details, but some of the features of these algorithms also allow leveraging the higher computational power of so I mapped out some of the things that have been happening since the 90s in these two fields. So on the bottom of the timeline here, I have the things that have been happening in data, and on the top of this, the clinical data research networks that have arrived since then. So this query model was introduced in 1993. The idea behind that was having an oracle that would distribute queries and implement these kinds of iterative methods that Shashan described to develop a converging statistical model across multiple different. Soon after that, cluster computing really started to gain traction, although a lot of the methods go back into the 60s, very early science days. Peer-to-peer networks started emerging in 1998. The book The Grid was published in 2000, and the first MapReduce paper from Google was published in 2004. Maybe someone else is going to correct me on some of the dates. So MapReduce has sort of gained a lot more interest. I have it bolded here. I think that this is sort of a landmark in terms of what is sort of attaining critical mass in the user community for distributed analytics and taking things out of what would be more of an academic space and into more popular use. Amazon came out with the cloud platforms soon after that. There's in-database analytics that has been developed since then. Azure is one of the Apache Spark project was launched a couple of years ago, and since then some other projects. Arvolution is a R platform that works on the platform, and I have down here Flora being published in 2013. And Flora represents one of the first cases where this approach is really focused on addressing the needs of clinical data research networks that have these very specific privacy needs. And so on the top here, most of you are probably familiar with these different projects. The HTML Research Network has been around for quite a while, but they adopted a standard data model that would allow them to apply these methods in the early 2000s. CA Grid is largely thought of as a failed, very large investment in cancer research that tried to implement a distributed network for cancer research. They were not successful at the postmortem has a number of different pieces. But one of the reasons was that it was very hard to adopt the grid technology around that platform. So going to the question of whether or not things are usable with documentaries, I think was one of those things that were a problem. I mean, time, AHRQ had the Distributed Research Network project launch, and Forum was one of the major side projects. I'm not sure the right way to put it, but certainly coordinated across all of that to facilitate these kinds of conversations. And this year, CoreNet launched, and that was 11 different networks for clinical data and 18 different patient-powered research. So how do we compare these two sort of converging bodies of work? A lot of times they're asking the same kinds of questions, but certainly different kinds of people are using them. So analysis questions in a lot of the big data user community is building patterns, they're trying to make predictions, trying to form classifications, business intelligence questions. In outcomes research, we're looking more aggressively at causal inference, which we'll hear more about later. Also, predictions. And so these are often kind of using use the same kind of methodologies, but have different types of questions. So the way that data are distributed in a lot of the data environments is can be controlled by a master node network, randomly distributed across different systems. This is definitely not the case when we're talking about federated clinical research networks, where you have heterogeneous data sets housed in silos that are not necessarily, in fact, almost never good. In big data, hundreds of nodes and there's tens of nodes in a network, if not research. The data governance constraints are very different between these two scenarios. The data set sizes in outcomes research are actually relatively small compared to the kinds of we're analyzing social network data and other kinds of transactional logs. The query distribution platforms in big data have fairly mature and are not very and are available in sort of products that are pretty widely advertised. So they have Apache Spark, Hadoop, MapReduce, Apache Basis, several other platforms that go into further specific for arenas, several more. Whereas we have a pretty small set of niche query distribution platforms in the effectiveness and outcomes research community. Shrine is the ICD2 for distributed queries, multiple sites. HotMeta is what CoreNet has adopted. Triad is another system. There's a few other also that serve mainly the needs of our research community. There's also a difference in the kinds of analytic platforms that are commonly used in research communities. I would say that our SAS data have been for outcomes research. Occasionally, hear people using platforms like MATLAB, actually not as commonly as I in my past life. The other issue is that the developer community is really large. Applications, and that's not the case in outcomes research. But I think that this issue here is probably going to be the biggest difference that we'll have to deal with either at a technical level or at a cultural level. And I think that we'll probably have to deal with the cultural problem before any technical problem will be resolved. So the idea behind this has been in place for distributed computing has been in place since multiprocessor available. This idea of having a master node distribute data and programs to worker nodes with each worker computing result returned to the master node and having an aggregation process. And for a sort of large class of algorithms, iterative approach would be this kind of iterative conversion to a single response. And since the early 2000s, this notion of having big data community working on quantity hardware instead of specialized hardware has created a certain So there's two components of the distributed computing that are focus of these courses. So there's a scheduling and distribution system to manage these steps of bringing the code together. One of the things that Shannon brought up was this issue of how do you add human in the loop to this kind of process when you're trying to schedule things that are happening in parallel across the sites. And the common platform here I mentioned before is Hadoop MapReduce to manage that. And there have been some more recent developments that sit on top of the Hadoop platform that have more efficient scheduling and more efficient memory. But the basic idea is that you need some kind of system to manage that. The other part of it, which I think is the hard part, is the programs for the local computation and aggregation. So at one time, the Hadoop platform required Java programming and some pretty specialized knowledge. And now Hadoop has a number of APIs that enable other languages to unify. So R, SQL queries, Python, and Scala are all languages that are supported on the platforms. And so these are the algorithms that have been.
So a little difficult.
Okay. So I did a sort of casual inventory of the different algorithms that people have published on open source frameworks. And I have Apache Spark, MapReduce, multi-core, Hadoop, and the federated clinical research networks. This is actually named referring to server. So you can see that there's a number of different approaches that are available. Linear regression, logistic regression, costs, the general engineer models, and broadly are available on Apache Spark. Need-based methods are those MapReduce Spark, King's algorithms, backpropagation algorithms, matrix factorization, which is often employed to do feature extraction using PCA or ICA, but matrix factorization is what was employed for Netflix recommendation algorithms. And see how the Netflix paradigm of making a recommendation based on a large data set might translate well into the kinds of recommendations we want to do in a clinical setting using leveraging large data that can start propagated. For other machines and EDM and other classification algorithms for us. So these are all things that are available in these frameworks now.
Danielle, are you willing to take questions?
Oh, yeah, sure.
Brian, did you?
Well, I mean, I have a couple questions, but one of them was, why the focus on Hadoop? Are you going to be dealing with a lot of unstructured data? So why? What's the justification for some of the frameworks that you talked about?
Yeah, so I should. So Hadoop isn't just the sort of unstructured KV. That's part of the Hadoop file systems and HBase management, and we also have the scheduler. So I should probably point this out a little bit better. It's the scheduling framework that the Hadoop offers, and there's other. Say that actually, so I would like to talk about today, trying to discuss how to bring structure to data using those aspects of Hadoop.
So is the main sort of research objective for this paper methods, understanding methods for sort of scheduled automated querying of a distributed network? Is that the?
So yeah, I would say that the question that this part of the presentation is posing is, can we leverage all of this work that has been done in the open source community and bring it into our environment, which traditionally has had very niche, customized, one-off software development projects. And so I think that the entire Hadoop stack may be useful. There may be other business projects as well. We have underutilized these kinds of resources that have probably overdeveloped custom software. So this is my proposal that so it just turns out, I think, that these big data methods are, it has to do with having these multiple network nodes and then that produce or master slave relationship. So in the clinical research, you have multiple independently operating data partners. And that's really the reason that we have this. In big data, it's just that it's really inefficient to rely on a very large processor further. You need to do it in parallel. And then the other feature of this distributed computation part of it is what Josh brought up in the clinical research paradigm. There's re-identification risks when you're transferring patient level data, and there's also risks that are associated simply with managing, I shouldn't say risks, barriers that are associated with managing liquidity. In the big data community, it's inefficient to transfer big data sets across the networks. You're able to manage these types of operations in place, you gain this computational relation. So this is just sort of going to your question, is can we better align with the big data community and leverage all the work that there's a lot of research methods that are supported by existing frameworks. Those are the methods and I guess going to talk more about these methods of the slide are more a matter of pre-processing data. And when I started digging into this, I felt paranoid about whether or not there was some validity problem like these things involved with this environment. And I called Jared and asked him to help me figure out what the reasons for management and so you can talk about it.
Hey, I just ask you one quick question.
Yeah.
A lot of those, say it as a statement, but I mean it as a question. A lot of those technologies, the situations where I'm familiar with the use cases is that they're primarily interested in the prediction from the model, not the coefficient. And oftentimes in our problems, we're actually, like you mentioned, statistical estimation as opposed to prediction. And like our causal inference problems, we really care about the data. We don't care about the low-level prediction. So I just want to comment about the applications of those technologies when we actually care about the model coefficient and what's been done in that space.
So I'm almost 100% sure that Jared is going to address so it's a good transition, but I think that that's one of the things that all the information that we would normally pour over when we're looking at our analysis outputs that have to do with what the errors are around the coefficients and what the values are doing the causal situation. That data is all present in these kinds of systems, but it may not be exposed to an interface where you can actually interpret the results or make a decision about how this is testing, for example. So I think that these are opportunities and making open source systems a lot more flexible than setting proprietary software.
And to follow up with Patrick, I mean, any time you're doing inferencing, it's a design-based analysis, right? So, you know, for prediction, oftentimes you can just take a variable prior to the outcome. So, I mean, do you guys present anything about automation of designs or anything like that?
No, not here, but I think we have done other work in doing that kind of pre-processing of data, so having the ability to manipulate those. Automating it, I haven't done a lot of work on it. I would love to.
Brian, I think that's really Michael's paper. It really is the design aspects.
Well, this is, well, it's both. It's analytics. Yeah, but you're right. I think you're right. Yeah. You probably need a working model for what the steps of the automation process should look like. Just new design and execution.
Before I get going, I want to thank Daniela for inviting me to work on this paper with her. She's been trying to get me to write it for 2 years, I think, since the day we met. And I'm glad we finally had a chance to do it. She mentioned briefly that she called me up and asked me about this issue of sort of structuring the data and whether or not that would impact validity by structure. So multiple clustering, right? We have data that lives at the institution level, we have data that lives at the provider level, data that lives at the patient level, right? All these different levels of nesting and clustering. And those are actually important. The first part of my slides is going to be trying to sort of convince you that those things matter, and it sort of sounds like from the discussion already that you don't need much convincing, so maybe that'll go fast. And then I want to talk a little bit about sort of ways we can acknowledge that and adjust our instances to take it into account. So like I said, clinical data that we're working with is sort of naturally clustered in these hierarchies. With multiple levels, right? Institutions and then clinics within institutions, clinicians within clinics, and then patients within clinicians, and then sometimes multiple observations per patient, right? We have happens over time. We have multiple things that we measure on patients. In addition to this sort of hierarchical structure, by cross-classification, I mean patients belong to these groups that aren't in hierarchies, but they sort of overlap, right? So think about geographies, right? Everybody lives somewhere. Formularies, right? Healthcare plans, that sort of thing. And then also demographics, race and gender, and that sort of thing. And all of these are sort of important factors for researching health questions. So the key issue I'm going to focus on first is the sort of hierarchical structure here, because I think it's got the sort of most meaningful implications for how we do statistical settings. So the basic problem is that units within clusters tend to be more similar than units from different clusters, right? That's sort of just obvious. People who live closer together tend to be more similar. People who see the same doctor tend to be more similar, right? Because they chose the doctor. They chose to live. And they did that based on all sorts of factors. So we have this correlation, inter-cluster or inter-class correlation that we have to deal with. Because if we don't deal with it, right, if we just sort of ignore that fact that some of these units are correlated and we use these models that assume that the data are IID, we're going to get wrong analysis, right? We're going to get standard errors that are too small. There's a stray data in there. We'll come back to him. But basically, the idea is that we don't have data that are independent. So we have sort of a smaller effective sample size that we might have basically. So this is going to tend to give us standard errors that are too small. It means that we're going to have confidence intervals that are too tight, right? We're going to be too overconfident. We're going to get wrong answers. It can also induce bias for beta, the parameter of carrot, whatever that happens to be, when, for example, treatment assignment is correlated with cluster membership, right? And this is sort of probably more the norm than the exception in these contexts. So, for example, Mike's going to talk about a case later on where patients have, physicians have different preferences for prescribing drugs, right? So that's the case where treatment assignment would be correlated with cluster membership at the physician level. And the other case where you can get bias is when the model is just dominated, right? And the patch just do it all estimated. So I'm going to sort of focus on a really simple model just to fix ideas. It's going to be a logistic regression model. So we have some binary outcome y, and the probability that yi is 1 is going to be pi. And then the logit of pi is going to be this linear function. So we have an intercept here, which I indexed by j bracket I. So this notation just means that patient I belongs to cluster J. Right, so that's the patient's doctor, right, whatever. And we have these cluster-specific intercepts. We have, which I'm going to come back to in a second, we have some covariate value treatment. We'll just say that's a binary covariate, and then beta is going to be the treatment, right? So if you receive the treatment, TI is 1, and then beta is the log odds of the outcome when you're treating yourself. So I've given the model these cluster-specific intercepts. Natural question is why would I do that? And you can think of this, right? So this is the sort of baseline rate of the untreated group. And if you imagine that we're looking at some sort of adverse outcome, say we're looking at stroke, and we're looking at that at several different sites that are distributed in space. So this is that sort of marginal prevalence, or the prevalence in the untreated stroke. That's going to vary based on site due to just simple things, right, like case mix. So if you're looking at a clinic in Miami that's full of old people versus a clinic in somewhere in young, healthy, vibrant California, right, those baseline rates are going to be different, and our model should allow for that. That's sort of cluster-specific facts or sets. So we're going to come back to this throughout this one. So I did just a little simulation study to sort of convince you that the clustering actually matters in a really simple case. So what I've done here is I've said, okay, I'm going to have 10 clusters. There's going to be 200 patients nested within each. Each patient is going to have a 50-50 chance of getting a treatment. And we're going to simulate outcomes from this model. Right, so I'm going to draw these alphas. I'm going to just take them from a normal distribution that's centered at -2. So it's sort of a modestly rare event. And then this beta is just going to be 2, right? So the treatment is going to increase the log odds. So I'm going to compute estimates, confidence intervals with 2 different models. So I'm going to use one that ignores the clustering and assumes a common intercept, and I'm going to use one that allows for the variant intercepts for cluster discussion. So if you do that, these are the results you get, right? So this is my pooled method, where I'm assuming all the clusters are homogeneous, they have a common intercept. This is the multi-level model that's doing the right thing, right? It's got the cluster-specific intercepts. So I did this 300 times, so each one of the points in this histogram is an estimate from one simulated data set. So if the estimate was unbiased, it would be sitting right here right around 2. Meaning that if I repeat this experiment over and over and over again, my estimate is going to be sort of wrong. In the model that doesn't allow cluster-specific intercepts, it's not, right? It sits in sort of the wrong place. It's also got a sampling distribution that's a little bit wider, a little bit noisier, because of the resampling the alpha Gs. So the estimate's biased. The confidence intervals are also wrong. So the other thing you can do is you can compute these estimates and get a standard error and build a confidence interval. If we compute what should be a 95% confidence interval and then just count up how many times cover the true value, your coverage rates. And for the pooled logic model, it's about 0.23 versus 0.96 for the correct model. This is unsurprising. This is sort of tragic, right? What it means is that I'm not doing very good on averaging most of the data sets actually.
So when you say biased, is it biased away from the beta TI or coefficient influence simulation? What's it biased from?
The true beta, right? So the truth is 2. So for any particular data set, my estimate is not going to be exactly 2. It's going to be some noise speed, a little bit.
It's the beta for TI, right?
The beta for yes, this is so this lack of coverage is not news. You fit the wrong model, you make the wrong assumptions, you don't get the right coverage. It's sort of endemic in these research settings. So the OMOP team has done some great work showing that most of the analytic methods we're using don't actually have the right coverage. They don't have p-values that are distributed uniformly, and I encourage you to look at that work because it's terrifying if you use healthcare. And this is just one of the reasons why, right? The analytic method that we're using has to account for this sort of data structure. And if it doesn't, it's wrong. Bias. Any questions? Please just jump in.
So I have questions, but there's probably no easy answer, right? So, you mentioned that you had interest in causal inference. And oftentimes in causal inference, the starting point is the causal effect estimate of interest. And it's usually represented in counterfactual notation and often identified as the average causal effect and the marginal effect. And I think that there's implications for that when you start to allow for differential slopes by the clustering unit, and you move away from a population average effect to something that people think of as a conditional or subject or whatever your unit is. So that's why I asked the question about what is bias. Because if bias is the average causal effect, you're generating bias by clustering unit. And if your target estimator is something else that's consistent with the model, then you have to be clear about what that is. I don't think all the counterfactual calculus is going to work out for these kind of problems. It's still sort of an open issue that needs to be dealt with. But bias is kind of a nebulous concept unless you state your counterfactual based effect estimator. Then you can sort of talk about bias from that effect estimator.
So two things. The first one is I have to apologize because I forgot for a minute I wasn't talking to a room full of statisticians like I normally am. So to a statistician, the idea of bias is that my estimates of the parameter should be centered around. Not to say that bias is used.
That's not a different statement, I don't think. I think that both the counterfactual based framework would use the same definition.
So it depends on whose counterfactual framework. So if you're talking about sort of Judeo-Pearl style, writing down graphs and talking about entire distributions of things, then probably that's true. If you're talking about sort of the Rubin causal model framework, in most contexts, the focus is really on finite sample inferences, and there's actually no model parameter that you're interested in. But leaving that aside, the point you think about interest in average causal effects is a good one because the question is the average of one population, right? In this particular case, I've sort of sidestepped that by assuming that the treatment effect is actually constant across the groups. It's just this marginal prevalence is different. So if I'm doing estimation right, I should be able to get the right answer here in this very, very simple limited case. And we're going to talk about sort of more complicated things, not specifically related to causal inference, but I'll come back and make that connection. Does that answer your question?
No, that's helpful. I think that the modeling, the estimator, to me the point is defining the estimator. Am I looking at a population average causal effect, subject level, conditional effect, local average treatment effect, type? And I think there's implications for that when you do the clustering and setting slopes, individual slopes across the
huge implications.
Yeah, that's one point I was trying.
Yeah, no.
And that really affects what you think of as bias. That's the way I understand bias.
Yes.
In a more epidemiologic causal basis.
Yeah. So in this context, I went ahead and I assumed that the treatment effects are homogeneous, so the clustering is not important. I know that to be true because I made a model and we have the data. These homogeneous treatment effects are probably not right, and we'll talk about that a little bit too. So now what? We have this clustering that matters. It's giving me the wrong answers if I ignore it. So what am I going to do? A very popular thing to do in econometrics in particular is to just sort of mess with the standard errors. Use clustering standard errors, Huber standard errors. I see nods, right? So it's the idea is that basically they inflate the variances in sort of smart ways, but actually the estimates I compute for the standard errors are unbiased. Standard variances are unbiased variances of that particular. These methods have some difficulty when you have unbalanced data. So when you have different cluster sizes, they don't always work so well. Non-linear models gets a little weird, right? These things are sort of built on OLS because so is econometrics. And then there's also sort of the more general, the Freedom critique, right? The model is wrong. You're adjusting the standard errors because you're fitting the wrong model. So maybe the thing to do is to fit the right model, right? So that's sort of notion for statistician for sort of grading on everybody's grade in a long series of papers over his career. And the other point I want to make is that cluster effects are interesting, not just annoying, right? This isn't a nuisance thing. I don't want to just sort of adjust my standard errors. I actually want to study some of this variation across clusters, right? The point about treatment effects varying across clusters, right? This is all interesting information that's meaningful and useful. So I'm going to propose that we don't just use clustering standard errors, that we actually go a step further and try to model these things. So one thing we could do is to forget about pooling the data, right? If we want to say, all right, things are heterogeneous, let's let them be heterogeneous. And so in the distributed analysis context, we might say, all right, I'm going to fit the model at each site. I'm not going to have a common, I'm not going to have any common parameters, right? I'm going to learn about these things from each site separately. The only application I've seen of this in this clinical research network setting is Darren Toth's work et al. Where they do just that. They say, all right, I want to learn about this model. I can't pool the data. So I'm going to fit the model at each site. I'm going to get parameter estimates. I'm going to collect them. And then I'm going to combine them. So the question becomes how to combine them. And so what they propose is you basically consider that each site's parameter estimates come from a separate study, say, and then you're going to apply meta-analysis. It's relatively straightforward to do. You compute your estimates, so if we're interested in beta J now, you compute your estimate at each site, and then you just take a weighted average. And the weights are given by a formula like this. So in this case, sigma squared J is going to be the sampling variance, the standard error of my beta at J, right? So that's just your usual formulas for that. The thing to know about beta J's is that, right, this about the sigma J's is that it's going to be decreasing in the sample size, right? As you get more and more data, those standard errors are going to be higher. So these weights are going to give proportionately higher weight to cluster estimates that have large sample sizes. Okay? And there's this extra parameter tau, there should be a tau squared, forgive me, that represents variance between the beta J's. In terms of this weight, it sort of normalizes the beta J's. So the idea is that if tau is really, really big, right, it doesn't matter what sigma J is, the weight's going to be constant. In that case, there's a lot of variability between sites. If tau is really, really small, we get something that's called a fixed effects meta-analysis in the limit where tau is just 0. We're just pooling these things based on experiences. And the assumption there is that actually this isn't really the model we want to be fitting. We don't actually believe there are heterogeneous parameters. We think they're the same. We just can't actually pool our data. So but the random effects meta-analysis actually makes this sort of allowance for, okay, the parameters are a little bit different, say. So there's actually a model looking behind the random effects meta-analysis. And the model looks like this. We imagine there's a true population effect, right? It's beta. And then we get our site-specific, true site-specific effects, these beta J's. There's beta plus some disturbance, plus a little bit of error, if you want to call it that, right? Between cluster variability. And that comes from, say, a normal distribution. It means 0. In the next level, we have our site level estimate, right? This beta hat J. So these are estimates of the parameters computed at each site. And we assume that that is a linear function, right? So it's centered at the true site level effect, this beta J, plus some estimation error. And that's going to be a constant. That's the model behind the random effect. We don't actually care about where these beta J's came from, and we just sort of ignore the fact that we actually have this. So the idea is that the sort of true site level effects are just sort of centered around the same place, right? This true population level effect. The normal errors, these delta, are just sort of the sum of a lot of little things that vary across sites. We don't actually know what they are, so we're just going to assume that they're normally distributed. There's some technical reasons to think that might be true, or at least not a bad approximation. Now, I'm putting this up here to show that doing the meta-analysis is more than just a sort of a hack and we can't fool the data, right? There's actually a model behind it, and the model makes a little bit of sense, I think, in these settings where treatment effects vary by cluster, or at least could, because we can actually learn a little bit about how much it varies. And that's meaningful. So some assumptions that are in this model, like I said, the normal disturbances. Not a big deal to assume that these things are normal, right? If we say that these deltas are sort of the sum of a lot of little shocks to the system, whatever, then it's okay, sort of plausible. This is usually justified based on some statement, right? Our estimators are approximately normal. Variants that we know, and they're always unbiased. Right, so we also assume that our site-specific estimates are unbiased and the standard errors are well estimated. Going back to our original point, that means you do still have to account for within-site clustering, right? The model we fit for each site needs to account for clustering by providers, by clinics, by whatever. Otherwise, you're going to get the wrong answer. And you also need sufficient sample sizes to be able to estimate these parameters, right? And if you're estimating effects that are that correspond to rare treatments, exposures, rare outcomes, small groups, right? You're not going to have enough data to just estimate these things sort of naively using maximum likelihood or whatever. And actually, in that paper, they run into this problem in their simulation studies where they have sort of moderately rare treatment effect, or sorry, a moderately rare outcome. What happens is you get sites that only see all ones, or they see all zeros, and you can't actually estimate the parameters locally. And their application wasn't a big deal. They knew the model that the data came from because they wrote it down, so they could just drop the sites, and it's not a big deal. It's important to point out that you couldn't actually really do that in a more realistic setting, right? You're going to have heterogeneous cluster sizes, and cluster sizes might be correlated with other factors, right? Small clinics might be different than large clinics. They probably are. So you can't just sort of drop data and expect things to work out. So then the question is, sort of what can you do? So if we go back to our running example, I've carried forward the cluster-specific treatment effects. These beta J highs now. So let's just say this is our patient-level model, right? I could have lots of other covariates in here. I could do lots of other crazy things, but we're going to just sort of illustrate with this model. Now, like I said, the within-site model parameters and their standard errors are not going to be estimable. All ones or zeros for the outcomes, and that's going to be fairly common, right? Just due to sampling variability when you have these rare treatments or effects or outcomes. So what I want to sort of promote is the idea that we don't have to choose between fitting them all to all the data, fitting them all to the separate subsets of the data. We can actually sort of interpolate between those two extremes. We can use partial. And I'm going to talk a little bit about how we achieve that. And this is basically how we do it. So I have my site-specific models now, right? This is the same guy from the last slide. But now I'm going to give these things distributions. So I'm going to assume that I have n sites, and my site-specific intercepts are drawn from a particular normal distribution. My site-specific treatment effects are drawn from another normal distribution. I'm going to learn these parameters alpha naught, beta naught, sigma alpha, sigma beta, these things from the data. And the point is that you end up interpolating between these two extremes of complete pooling or no pooling, right? If I take the variance parameters down to 0, then these things are going to be the same across sites and we're back to complete pooling. If I take them out to infinity, I'm going to do no pooling at all. And I'm going to estimate them separately for each set. The intermediate values will achieve partial pooling. A couple things to say about this before I move on. I have a frequentist in the room, so I should point out that this thing was suspiciously like a Bayesian method, and it kind of is. You can also motivate these things in terms of penalized likelihood, and have very good frequentist performance. So if you do this Bayesian procedure over and over again, it actually does pretty well on average with repeated data. So in the picture, this is sort of the effect that you get. This is an example from Gilman and Hill, which is a great textbook I would encourage everybody to look at. And these this is an example he has about estimated radon exposure home, so the actual context isn't that important, but the idea is that each dot is the estimate within a cluster, in this case they were counties in particular state. The bars are standard errors for that particular estimate. And they fit two models, one doing no pooling and one that's a multi-level model that's doing partial pooling, like I described on the previous slide. So in the no pooling model, you get some sites, so down here, they're ordered by the sample size, right? So as the sample size gets large, they're really precisely estimated, the standard errors go down. When the sample sizes are small, the standard errors are huge, and there's just a lot more variability in the effects down here, right? And we can, there are suspicions that actually some of these really extreme values are probably just noise. Probably just due to small sample sizes. So the idea is that you want to sort of regularize that with a multi-level model. And so if you look over here on the right, where they fit this model that's on the previous slide, what you've done is you've taken these sites where you don't have very much data, and you just sort of shrink them back towards a common mean. You're saying, I don't really know anything. I don't know much about these sites. I know that the effect is similar than it is different, right? And I have some notion of how much the effect actually varies across sites from up here, right? From these places with a lot of data, where I can get a really good estimate for the within site. I can get really high precision estimates for the within site effects, and I get an idea of how big the variance is, and I sort of map that down. And still imprecise, but it is what it is. And so you can see, so for example, this point that's circled, right, T, it's pulled down here. It's probably not so high. Most of the effects up here where we actually have data that are not so high. So we're going to bend and shrink that to a common. So that's the simplest multi-level model you can fit, basically varying intercepts, varying slopes. More realistic model would have all these levels, right? Anything that's important for the outcome potentially. Institutions, clinics, clinicians, patients. You might have covariates at different levels. So for example, one reason that your treatment effect might vary across clusters, sites, is that background covariates might vary, things that we can't measure. So for example, patient incomes. I'm usually not going to have good data on that, but I might have good data on site-specific incomes from the census, the ACS. And so I can actually adjust for that, right? The idea is that in low-income groups, maybe adherence is poor, access to other care is poor, maybe all these other factors sort of combine to produce, sort of, on average, more outcomes in that group, less favorable outcomes in that group than in, say, a wealthier group. And I can actually adjust for that if I have that information about the sites. I can include them all from my actual covariates. Another thing that this kind of shrinkage lets us do is estimate deep interactions. So maybe I want to know, do treatment effects actually vary by sex and age and on and on and on, right? Some reason to think that maybe it does. I'm a statistician, I don't really claim to know, but there seems to be a sense that maybe these things do. But the problem is once you chop your data into these really tiny buckets, right, we're back in that small sample setting where I'm going to get really noisy estimates. And so I might want to say, well, I think that it's possible if there's a race by gender, by age, by whatever interaction. I know that my data can't tell me everything, so I'm going to say, a priori, those things should be similar in those different cells, but not the same. And then I can actually sort of learn about that. And I think this context of working in these federated research networks is a case where we actually have enough data to start estimating these interactions. And they're important for a couple of reasons. One is that we might just be interested in studying these subgroups. Another is that these models that condition on a ton of variables are really useful to do something called post-stratification, which is a way to map estimates from one population to another population. It saw its sort of birth origin in survey statistics, where you sample from a population that's different than a target population. You compute those stratification weights. But to do that, you need an estimate within all those little groups. And multi-level modeling gives us a way to estimate sort of coherently and efficiently the effects in those subpopulations.
I have another question. You know, I'm really not being critical. I think it's a great presentation. I have a lot of gaps in my knowledge about multi-level modeling within the way I try to think and also time training. So is there any guidance for how cluster units should be selected and modeled based on concepts around confounding versus just, you know, unstable estimates? Is there any, you know,
there's a lot of fighting in the statistical literature. More disagreement than consensus, probably. So for effect estimates that are unbiased, it's difficult to do in these contexts. Right? One aspect of the shrinkage is that it induces a little bit of bias, and it does that to get better variance.
But I mean, is there, so how do you think through, you know, at least there's a framework to think through how you include variables into a statistical model, a typical traditional, you know, simple model, to remove, you know, confounding type models, right? And so the type of bias that you're focusing on in the multi-level model is imprecision for the most part. It's not, you know, missing the target necessarily. So how do you, maybe there's not a clear answer, but it seems to me that the type of information you put in the model, the clustering unit, should, you know, probably has to, you know, be framed as something that can be a source of a common cause or something like that as well. There's probably some way to think through that.
Sure. You don't want to be capricious, right? So I mentioned a lot of different ways that observations are grouped in these policies different levels. There are some of my more ambitious colleagues would say you should include them all. You know, we should fit the most complicated model we can. The problem is that the most complicated model we can is the one that comes that includes all these.
So are you focused on like problems outcome, or is this mostly
generalizes to generalized linear models, to nonlinear models, linear models, sort of all over the place. You know, the basic ideas don't change much. It's just it's very clear in the logistic regression setting what's going to happen when I don't have a lot of data, right? I'm going to get complete separation and I can't estimate. But there are sort of analogous things that happen everywhere in linear models all the way to more complicated algorithms. So I think there's two things. I think the one point that we agree on is that when you're estimating a causal effect, you need to be really precise about what population you're estimating it in, and how you want to do that. The thing of it is that a lot of these settings, you know, we're estimating the causal effects in convenience sample, right, of the sites that I can get access to. It may not correspond to something that I care about. You know, I might want to know what happens if I roll out this treatment at my clinic, right? In which case, multi-level modeling is really the only way to get at that because it includes a distribution for these sort of site-specific effects, as opposed to a fixed effects analysis, which can't do that, or complete pooling, which just worse. So yeah, there's a lot of work to do on that end, but I think that these are promising. I'm doing on time.
I wonder if we could just save this kind of discussion for the breakouts.
Yes. Okay.
We can get the person who goes next.
Well, yes, we'll barrel through this. So I have a few slides on actually fitting these things in federated networks. I don't know. I kind of want to hear what Mike has to say more than what I want to say, so I'll be very quick. The sort of popular methods for fitting these things are iterative. They're computationally intensive. There's a lot of communication back and forth. It's going to be difficult for the reasons we heard about earlier. They take a lot of information, particularly when you're doing fully based thing. So they've been problematic. There are some very, very recent developments coming from really smart people at Google and how you can actually fit these multi-level models approximately without pooling the data and without doing a lot of communication. I just want to point out this is Steve Scott and his colleagues at Google proposed this algorithm. Right? So the problem is that we're communicating between machines at all. And it doesn't sort of matter how you do it, right? They've looked at all these various factors that slow things down in parallel distributed settings. decided that none of them are really important, and you know, to actually be able to fit these multiple large data sets, you need methods that are very selective in the way that they talk back and forth between states and messages. Well, that's unfortunate. So the idea is very similar to what Danielle was talking about. In the particular method, they send the data to the nodes. Each node computes the posterior order local parameters and global parameters, takes the estimates, samples from global parameters, and send them back to a master node who combines them and then propagates them one more time. The point is that there's two sort of iterations of communication instead of multiple in something like PCOR, where you're doing back and forth. Any iteration you're on. Two iterations. Other possibilities I'm not going to talk about too much. I do want to point out Explorer, which was sort of a core extension, modification, however you want to put it, that's using a similar sort of algorithm to some of these variational-based methods. The idea is that it's sort of more robust to asynchronous communication to small nodes to the problem of having to stop and wait while the site computes the summary statistics and that sort of thing. And these variational Bayesian methods that are sort of coming out of the literature now are both suitable for large pooled data sets and also large multi-level models. So a lot of promise there. The take-home, you know, we have a real opportunity in these federated research networks to learn things that we don't know. If we're going to do that properly, we really have to account for the structure of the data, which is actually informative on a lot of things we care about. I think multi-level modeling is a good way to do that. I think you can get us estimates for a lot of things that we can't estimate otherwise. But actually doing this, actually fitting these things in distributed settings, it's going to require extensions to existing frameworks. It's require work built on, you know, whatever, either some of the existing work or some of the open source methods that they are. So I'm going to stop. Thank you very much.
Section, so I want to ask you questions.
Okay, so my presentation is going to be in a couple of respects. One is that I'm covering a much broader territory, rather than talking about specific methods and really trying to sort of set all these methods and designs and so on in context. Basically, to try to get this, address the question of how do we learn in the learning healthcare system, and try to bring some perspectives together. The second thing is that I'm acutely aware that everything that I wrote about and will soon speak about, somebody knows far more than me, and most of those people are in the room today, so I'm not going to try to get everything right, but simply try to lay out the field that we'll be talking about, and then, of course, we'll be turning to that in the breakout sessions that start right after this. So, the background for this is that, as we've seen in all the work we've done in EDM forum and elsewhere, that the existence of electronic clinical data really has the potential to advance our knowledge. And you can see all the different things that people have said. Sebastian Snavelice has an article in today's New England Journal making the same points as well. And in fact, some people go so far as to say, now that we have all these data, we don't need to do randomization anymore. I think that's a pretty far out assumption. But setting that aside for a moment, I want to point out that despite the enthusiasm, none of this is easy. It assumes that the data are right, that they're, and that without randomization, without randomization, we have biases that don't go away by getting more data. And so we come back to the question about RCTs, which are generally regarded as the gold standard in health research. And you even have things like the article in New York Times back in February, where people, Gene Cloud, quoting people saying, well, you don't randomize, we don't know anything. But on the other hand, you all know that you can't do RCTs in some settings. And when you do them, you have problems like they're very homogeneous populations and make it difficult to extrapolate. They may be strong for too much validity. For some questions, you can't do RCTs at all, safety issues and so on. I guess I particularly want to stress the impact of delivery system changes when we make changes at system level rather than individual level, which often is very hard to randomize for a number of practical reasons. So that leads us to the question about observational studies using existing electronic clinical data offer the opportunity to investigate interventions and outcomes, and sometimes at lower costs. Strengths are we have large, diverse populations under observation. We have relatively complete information, and this is improving over time in the electronic medical records on both the treatments administered and the health outcomes experienced. The reporting bias may be minimized in favor of some studies because it's data gathered in the course of care as opposed to recall bias and so on. And the data are there already in electronic form, which could conceivably and quite likely lower costs quite dramatically. The weaknesses of observational studies are due in part to the lack of randomization and the possibility or the likelihood of selection bias and confounding. Also, because these data systems weren't designed as part of studies, you often don't have all the information you need on confounders that would help you to adjust for some of the biases as well. And data issues are more often a problem as well. There are ethical and privacy considerations, and so, but really the focus of what I've been trying to do and what I'm helping is how do we balance the rigor and the internal validity of RCTs with the relevance and external validity of observational studies based on electronic data. How do we come to some? And I think maybe we want to think about observational studies as complementing rather than replacing RCTs. So what I've tried to do, the first draft of the paper, brings together approaches from a variety of different perspectives. The first one, I think that really represents what we've heard about so far today, is methods for the analysis of individual level of data that come from metrics and other fields like that. The second group is methods that derive from the social sciences, things like interpretive time series and natural quasi-experiments and so on. These also fit neatly into these categories, I should say. And one of the things I think we want to talk about is how to organize it. But just to give you a sense about some of this. And the third perspective is the quality improvement, delivery system science perspective, and so on. So I've got something to say about each of these things and how they address some of these issues. And even as it turns out, particularly when we get to this quality improvement area, what are the questions? The question isn't simply does it work, but in what populations, in what circumstances does it work, and what can we learn from that? So the goal for each of these methods is to talk about how they control threats with validity, particularly ones that would have been addressed with randomization, and analyze the strengths and weaknesses for particular uses and summarize some of the best practices. We can't covering this much territory. And the way that I'm going to do it is to take a step back and think about RCTs as a model for observational studies. What is it about RCTs that makes them so useful that people think they're the gold standard? Some of the things that Cochrane laid out in 1965 here are shown here. Partly well-designed studies in the general sense. Those are things that we can address. And then that leaves us with finding ways to adjust the differences in observed characteristics between the groups that would have been taken care of with randomization, but we had to find out, including knowing what counterfactual, what would have happened if these patients hadn't received this treatment. And the counterfactual is important here. Things about RCTs is they tell us what the counterfactual would be, and because they're assigned at random, we know that there are no systematic differences between the treatment and the control. This is important because at the individual level, the way that people respond to medications and other interventions varies quite a bit. People get better spontaneously with no treatment. Sometimes the treatment doesn't work for certain individuals. You generally can't say if Mike didn't get the drug, we don't know what would have happened to him. We just talk about this, what happens in groups of patients. Now, sometimes the counterfactual is pretty clear. And there's a famous tongue-in-cheek article written about a decade ago about RCTs and parachute jumping. No one would do that because everyone knows what would happen if you jumped out of the plane without a parachute, right? But there are other real examples, and I give the Peter Provost Michigan Hospital check this study as well, where they had the hospital-acquired infections working away at a high, relatively high level. They did an intervention and it dropped to zero and stayed that way for a year and a half. And it's kind of hard to say, well, it probably dropped it to zero for something else, some other reason other than the intervention. But of course, that's the judgment that you have to make. And things usually aren't so clear. That's part of what we try to address with some of these designs we're talking about. The other thing about assessing cause and effect I try to look at is, from Dick Goodman, I got this idea about contributory cause, the idea that cause precedes the effect, and randomization gives you that because you have to manipulate things and you have to get it. Secondly, that the association between cause and effect is there. The randomization makes sure there are no systematic differences, and that makes it there. But the third one, which we often don't think about so much, is that randomization involves a deliberate allocation of treatment and control. Somebody goes in and interferes with the system and breaks some of the assignment selection biases of someone that we see otherwise, where we actually, when we talk about quasi-natural experiments and deliberate system science, where we do make a deliberate change. And I think we have to find ways to learn from that. One example is smoking and lung cancer, and the Bradford criteria apply to that. Epidemiologists have thought about this issue about assessing causation from when you only have association for years, and there are ways that we can do it. I'm not going to go through the details here. So when we're talking about individual level data, we have to realize that the potential for bias is that the groups don't have the same risk for the outcome. So there are a number of ways that you can think about doing this. One is selecting data sources and patient populations and inclusion and exclusion criteria for which the bias is likely to be minimal. And I've got some discussion about that in the draft paper. Secondly, and this is what most of the attention among statisticians tends to be on, is ways for adjusting for bias and confounding through different regression approaches, instrumental variables, propensity score methods, DAGs, and analyzing observational data like RCTs, which I got from Randy and Elaine, excuse me. But there are also epidemiological designs, study designs for individual level data that I try to bring together. And the time that I have, I'm not going to try to go through all of these things. But again, the fundamental problem here is to try to understand is that no one can get both the treatment and the comparison. And randomization gives us a way to know the counterfactual. We have to find some way to address that. And each of these methods makes different assumptions to get to that answer. And sometimes these are obvious, and sometimes these are obvious to people who are well trained in these methods, and then gets lost when they're presenting it to others. And so one of the things that I've been trying to do with this paper is to kind of clarify what these assumptions are, get a sense about when one method may be more appropriate than others. I think really the way to deal with this is to recognize that all these methods have assumptions, and to the extent that you can test those assumptions, or maybe even try different methods on the same data that would rely on different untestable assumptions, you may get a better sense about how robust the results are to those assumptions. Okay. Let me stop and take a breath now and see if people have questions about that.
I think that the point that you're raising about the need to characterize the counterfactual is a really important point. One of the things that I see as a challenge for the community is we distort what the counterfactual is when we start to talk about a comparative effectiveness question. Because in an RCT where we're thinking about unexposed to intervention, as compared to an alternative intervention, which may also have its own effect on the outcome. I guess I'm bringing up this comment because I don't get the opportunity to be in your group. But I wonder whether there's an opportunity, because you're highlighting that, I think that is kind of the crux of the issue, but there's an opportunity to try to really clarify what is the counterfactual in a randomized trial context, and what is the counterfactual in a comparative effectiveness context, when they're slightly different, and the assumption that lack of exposure has no association with outcome actually gets violated when we're thinking about alternative treatments that directly impact the outcome.
I think that's a really important point that I don't bring out enough, but I do need to bring it up. It reminds me that epidemiologist I was talking about, some of the famous epidemiologists who made a career by asking the question, compared to what? which we often don't answer. We can also even raise that question. That's essentially the question you're asking. Being more explicit about that, I think, can be very helpful.
In a logic context, when we think about a new user cohort design, when Wayne Ray was proposing that for pharmacology 94, part of the argument was that using a active treatment for a new user comparator was simply to try to make the groups as similar as possible without initiation of therapy, but there's an implicit assumption that the comparison, the alternative treatment, better not be associated with the outcome. When we start actually asking the comparative effectiveness question, very oftentimes the comparison is supposed to have an association with the outcome, just differential from the treatment of interest. And so suddenly the motivation for the new user cohort design in the context of pharmacoepidemiology and safety, when there was no association, suddenly gets blurred, the lines get blurred when we start talking about
and being clear about those things in your head can help you realize that this method, this design, is better than some other one, because they address that. So part of what I'm saying is just think these things through.
I think another point that I'd like to comment on is one way to try and have people not object, for example, to observational studies is to say that, look, it's the scientific method requires you to observe first. And there are a lot of things that you don't want to test immediately, but you want to know what the set hypotheses or the plot. And I think observational studies is exactly the right place where you don't need to have a counterfactual or something to compare or something to test. You just want to see what is happening. Because too often our policies are based on hypothetical assumptions about the world, and when you go and look at the real workflow, the real problem is just something totally different, and you base your RCT on garbage.
Yeah, I think that you're right. That gets at the issue, what's the question? And sometimes they are generating hypotheses about things, generating ideas. But also sometimes you can think about them, and so we get into this in the last section of the paper in quality group. It's often you have an idea, and what you're trying to do is figure out where it works, under what circumstances it works. And so it's important to have in mind what's the question, because otherwise it's embarrassing.
Could you also just one more thing about sort of the ethics of this whole process? So when I speak to some people and read some papers, it sounds like one of the reasons for the RCT is because you're worried that, oh, people are doing weird stuff, meta-analyses of the data, and therefore they're cheating by presenting, in papers false results. And in some sense, if people were just more honest and connected to the workflow, in some sense that dishonesty part is thrown out, and this objection of RCT, the gold standard, kind of countered, because you can take observations and you know exactly how it's collected. Good analysis on observed data as with randomized controlled trials, maybe better sometimes, because it's collected totally at random and has no bias to pre-written.
So Mike, I totally agree with the counterfactual argument is really the fundamental aspect we're talking about here in terms of the need for randomization, actually, and that not all comers come to the healthcare system, right? There are those that don't come to the healthcare system. Those are the ones working with our observational data sometimes. But Mike, could you go back a slide? A couple of the things that you talked about here. Maybe one more? Yes, sorry. Yeah. So we talk about all these methods, we've gone around the block, a million times, but the one I think is most promising is the instrument variables, because that approaches randomization. But there was one of your slides that talked about we need to look at how to randomize like within an observational data set. There are a couple of them that really piqued my interest as to what we should be looking to try to improve.
Can I ask that you say that the breakout session?
Absolutely, I will. That's what I'm pointing it out, was that I'd love to talk about that. I think those are great topics.
Yeah.
Just so a general point that you get into quite strongly in the next parts that you're going to talk about, but which I think would benefit you in these first two areas, is the whole idea of clustering. Because a lot of the work that you do, as the point was made in the last session, you're dealing with clusters, and RCTs in the context of a cluster randomized trial, the assumptions about the counterfactual don't necessarily hold. In fact, randomization, with the numbers of clusters that we typically work with in the model, the world work doesn't guarantee balance between groups, and you get not only differences in the level of whatever outcome you're measuring, but also the trend of the outcome. So RCTs aren't necessarily the same type of gold standard in the work that we're talking about that they are in clinical trials. And,
yeah.
Then, and second, and then, following through that in the work that you do on individual other models, but bringing in the context of clustering, as was described earlier, the need for more sophisticated models, even in the context of individual trials.
I made a note as Jared and Danielle was speaking that having to incorporate that.
So you can certainly tell me that this is more for the discussion later. I wanted to play a little bit of devil's advocate to Patrick's point, just in the sense that the counterfactual, I guess the question you're asking, right? Because the counterfactuals in something like the comparative effectiveness question absolutely are different, and they make it more difficult to isolate an efficacy question. But from out here in the swamp where I spend a lot of time, those are the counterfactuals you're dealing with, right? And so part of the utility of these kind of methods is that we have culturally, for lack of a better word, developed a really deep expertise and a sort of tight linkage to efficacy estimates into methods that really propagate that well. One of the things that's exciting for me here is trying to figure out, okay, where can we, I'm not going to say we're just as good, I'm in the wrong room for that, but where can we do kind of applied effectiveness work in a way that lets us start to ask questions about those real-world counterfactuals and understand where that's going to change our inferences, rather than saying we can't go there because the inferences are not as clean.
Yeah.
I double disagree.
Yeah, no, I think that the comparative effectiveness questions are probably more valid and are more relevant clinically than a lot of the RCD questions. I think it's simply very important for us to communicate when we talk about a counterfactual
what is the counterfactual and how it might be different.
So I absolutely agree, and I'm not even sure that they're more relevant. They're just answering a different question.
Right. The notation works perfectly for comparison of multiple treatments. You view it as is there a difference in any level of treatment, right? So it could be treatment level 1, level 2, level 3, A versus B, it could be anything. It just becomes the language is difficult to make, but the mathematical notation is not.
So let's say this for the breakout. The next section really has to do with methods that I think is coming from the evaluation and social science world. The first one. And I taken from people's work in this group. Dennis is here. The idea about time series and how we learn from models like this, by fitting models that, presuming here that the counterfactual, after you've made the change, is for this to have continued in that way. You use the linearity within these segments to help you think through the counterfactual, and therefore to make estimates here with regression. So we have various kinds of threats to validity and threats to reliability of these designs that can be articulated. And I think that the summary of this is the advantages are that you have an intuitive visual display that helps you, in a way, communicate what you're doing, what are the assumptions you're making, direct estimate of the effects, and common threats to validity are controlled. But some limitations are it only works if you have a reasonably stable series and long enough number of observations, and sensitivity to some of the endpoints, and if there's no patient level adjustment. Quasi-natural experiments, the analysis of them is a generalization of this, because rather than just looking at one time series, you think through what else can be measured to help you understand that. The distinction between them is a quasi-experiment. They both involve always potentially change that involves health outcomes. Quasi-experiment is that the implementation was done within the control of the researchers, but couldn't be done with randomization. A natural experiment is where the intervention is done unrelated to totally beyond the control of researchers, so they can't randomly assign treatment to some and not others. And both of these focus on situations where an assignment breaks the usual links that could lead to selection bias, recursion, and things like that. So the advantages of this is they capitalize on deliberate policy changes unrelated to factors that influence the outcome. Cause precedes the effect, and you also have a situation where you observe changing the cause to see whether that leads to a changing in the effect. And if you have good tracking data that's generated for operational purposes, without you can minimize observation bias and be able to get an estimate of what the counterfactual might be. Now, of course, the disadvantages are you can't attribute the effect of the policy change. You can't attribute the effect of the policy change as opposed to something else that might have changed. And it doesn't tell you what the policy change made. That's true. I ran my short trials too as well. I guess I should say. And you can strengthen this in a variety of ways. One is to use a logic model that makes it clear, what you expect to change and different things, not just the final outcome. Use quasi-experimental design, find settings where exogenous changes are unlikely and appropriate controls. Multiple measurements, both pre and post the intervention, and this is where the time series comes in, but also not just the one data series that you think was as the outcome, but others as well. I used in the paper an example that Summers and colleagues from Harvard just published looking at the impact of the Massachusetts healthcare reform, Romney care, as we call it now, where they look not only at overall mortality, but specifically at healthcare amenable mortality in the adult under age 65 range, where you expect most of it to show up. But they also tie that into data that shows changes in access to healthcare, access to insurance, self-reported health outcomes, and it all fits together in a way that you might imagine. And then I sort of bring up here some of the work on qualitative analysis that comes out of the same perspective. That really helps us to, I think, answer a different question, not about whether or not something had an effect, but why. Understand what's going on here. And recognize that there are some well-accepted systematic methods for doing this. And sometimes when people talk about qualitative method, they tend to talk about mixed methods, excuse me. They tend to talk about analyzing individual level data. I'm really thinking here about case studies and understanding what happens when you change the system, and so on. And real health evaluation is a particular term here that I think bears a lot of attention to help understand how the context and the mechanism coming together leads to the outcome, and how we could use this approach to build up data from different settings and try to understand what works in what circumstances. Again, right at this moment, but that's something that we can talk about in a breakout session. So again, the strength of some of these methods is that they study the impact of deliberate intervention in real-world settings. The primary question addressed by them is estimating the counterfactual. What would have happened if the information hadn't been implemented? In terms of time series methods, do this by careful statistical modeling of the observation before and after the intervention. And natural and quasi-experimental designs extend this by repeated measures to study the functional form effects, comparison groups, jurisdictions, and settings, and outcomes, and multiple design elements, and maybe multifactorial designs fits in this as well. And I think it's really have a logic model. Everybody's got some implicit logic model in their head, but when you actually lay it out explicitly, you have to realize that people are making different assumptions. That helps you to think through what really makes sense to measure and kind of comparisons that will help you get to that, get to the answer that you want to have.
So I want to bring up this question of our observational data collection. Typically, we don't capture a lot of the metadata about policy change or things that might be actually used as variables, like the way the user interface might manage one treatment better. Yeah. How do you propose that we could build those logic models into the observational data collection workflow in a way that we could actually apply more broadly?
Well, let me address that in the next section, because the paper from Gareth that I'm going to quote from really addresses exactly that issue. I think it is an important issue. I think you're right, but we often lose track of those implementation details, which are really important in trying to understand, particularly when you don't have randomization, to understand whether or not you can attribute a change to the intervention. But even more, in trying to say, what does this mean? You know, under what circumstances could this apply? And also comes back to the question of what actually was the comparison to some degree as well. Because it helps you articulate those things.
Yes. I don't want to get into too much. I know I want to save this for the breakout, but implementation also matters for in rapid cycle evaluation. So we talked about that a little bit in the paper, and I felt that, and we can get into this more, but that if we do want to look into the data if it's readily available very often and reanalyze, we have to make sure to incorporate intermediate outcomes. But in addition to that, sometimes it's not possible to look so many times. Sometimes outcomes don't change fast enough, and all we have is implementation. are we doing what we're supposed to be doing? Fidelity, we're going beyond fidelity and looking at, is what we're doing feasible, does it make sense? And so on. So I don't know.
And I would say that's why you need a logic model. It helps you sort those things out. Exactly. Germany, you hear that? Well, by the way.
Thank you. Well, in your overarching evaluation method scheme, are you drawing a distinction between clinical interventions, so comparative risk research of drugging, CP, diagnostic testing, or CP, something of that nature, versus implementation research, which tends to be more context-sensitive, local issues and workflows play a bigger role. So I guess the bigger issue is there's more generalizability for CER type of evaluations versus implementation.
I think that's a really important question. I hope to address both in this. But one thing that when you are thinking about that, methods are appropriate in kinds of settings. I mean, things that when you're talking about individual level interventions, like giving one patient a drug and so on, or treating them in a particular way, RCTs are really important there because you have so much variability within people and what their response would be. And they're also possible there. When you're talking about changing a whole delivery system, the opposite is true. And it really calls for, I think, a whole different set of measures, and also a different set of questions that come up there. So let me use that as a transition into the final section here. And this is delivery system science from Lucy primarily here. Some of this is what we're talking about. We typically are, the IHI model for improvement is often what's in people's minds when you study something, and here science really focuses on identifying what might work. And then you do it, and then you do a control chart, and you see whether there was a change at the right time. That's an instructive concept analysis, of course. Again, the point here is that there was a deliberate intervention. So there was a very nice paper by Will Schrank that came out a year or two ago about CMMI's approach to the Center for Medicaid Medicare and Medicaid Innovations approach to rapid cycle evaluation, where they talk about a lot of these ideas. So I won't repeat the whole thing here. But one thing that they point out is that many of the innovations that they're talking about involve system level changes, where you really have to think about the evaluators as part of the system and helping them to look at the intermediate steps and figure ways to change them to make them better, and not wait until you have a 5-year evaluation of the overall implementation. That's a whole different paradigm from what many of us grew up with. And I think it's important to recognize that it's a different paradigm altogether. And so the lesson, I'll just end on a summarizing a paper Gareth Perry and his colleagues did about evaluation of healthcare improvement initiatives. The idea here is that fixed protocol RCTs are ill-suited for healthcare quality improvement initiatives because these initiatives are complex and context-sensitive. They're iterative in nature, and they vary depending on whether or not you are trying to develop the innovation in the first place, to test it, and to spread it. And more fundamentally, the question is not does it work, but rather how and what context does the new model work, or change be made to work. And so what you really need here is theory-driven formative evaluation, we say, and I agree, that considers the full path of the intervention. And again, this is the way you're repeating in a different language. The less perspective I was talking about here. And the point that they make is that evidence for the effectiveness of an intervention is typically based on studies in a small number of settings, where the full range of complexity may not be fully understood. But whatever work there is translated into a fixed protocol and then done in lots of other places. And then what worked in these original settings will work in far fewer settings that are different from the first one. And this is a graphical example of this is that as you go on through time, what worked well here, when you get into a wider set, may not work quite so well. And so the challenge is as you broaden your context, is to figure out what works in those other settings. So it's fundamentally a different question. And that leads to, so the strength of this is that it studies the impact of deliberate interventions in real-world settings, recognizing that fixed is not suited for this. It requires a stage-specific evaluation approach, rapid cycle feedback, qualitative as well as quantitative components, and a real evaluation perspective. The kind of stage-specific approach, and this comes from Garrett's paper here, is that the innovation phase, the aim is to generate, to discover a new model of care. And you really want to use quantitative estimates of variations in content theory and qualitative interviews to understand the underlying concepts. As you test it in a wider variety of settings, the goal is to test whether a model works or can be changed to work in other contexts. But here you want to have quantitative estimates of variations in the content theory, the specific contexts, and you can use things like the time series and control charts, set wedge designs, but then qualitative interviews to understand how the teams that are implemented in that context and what that means for adapting to other places. And in the improvement phase, the aim is to assess whether execution theory worked or should be amended for increased uptake. And here you're using primarily quantitative methods, process measures. You can measure process because you already have a good sense that doing that process will lead to the intended outcome because of all the work that's done before. And also, to some degree, the overall impact and the unintended consequences that you play out in more and broader settings. So, again, that's a lot of stuff that I tried to cover. And the goal is to really dig into it. And I'm hoping to we'll treat this as a collaborative process. So we try to understand each other. Many of us come from one perspective, and the goal is to try to look across those perspectives, see what they have in common, and what we can say about when different methods are appropriate in different contexts. So, okay. We're far over the intended.
Yeah, right. So it's 11:45. Shoshan, I was going to ask you, so we initially had time for a fairly lengthy breakout session first,
right,
followed by a networking lunch. We're almost at noon, so right, we could potentially shift things around, but I don't know what you think.
I think we can do the network lunch first and then come back in the afternoon for the breakout.
Would everyone be all right with that if we break for lunch earlier and then have a, and this is a good opportunity to kind of say hi to everyone, right, and then we'll, and then maybe if we come back at 12:45 when we were originally scheduled for lunch and move into the breakout session, sure, then we can.
How about we come back at 12:30? That'd be enough. 45 minutes.
If we just go through the smart map next to it, we can do it. Yeah.
Okay.
Yeah.
So great. Do you want to give us instructions for lunch session?
Oh, sure. So when we get out of this building, I'll direct people to the smart map. So it's a small coffee shop, and we can get a brief lunch from there. Great. And after that, actually, we have two breakout rooms at the third floor. On the room 4, we'll go to room 3.